So in the last video we talked about linear approximations. Sometimes those are looked at in terms of what we call differentials. So if you have a function f of x, then the differential dx is an independent variable. The differential dy is then defined in terms of dx by the equation dy is equal to f prime x dx. So basically dy is like saying how much is my y value going to change if I change my x value by a certain amount. It's most easily seen by looking at a visual. In this picture here, we have a curve and we have a tangent line. The dx and dy represents or corresponds to the tangent line. The delta x and delta y corresponds to the actual curve. What dx and dy, or let's start with delta x and delta y. What delta x is saying is, if you change your x by that much, delta x much, so maybe that's some small number, then your y value of your actual curve will change by a certain amount. That certain amount is delta y. So a small change delta x in your x value will create a small change delta y in the y value of your actual function. Now the dx and dy, that's saying dx, a small change in your x value, will cause dy, a small change in the y value of your linear approximation. So dx and delta x, you're changing x by the same amount. The difference is when you're working with the deltas, that's the change in the actual function. The dy is the change in the linear approximation. And just like we talked with linear approximations in the last video, sometimes delta y may be really difficult to calculate, and it's much easier to calculate dy. So as long as you're not changing x by too much, if that delta x and dx are really small, then it'll be much easier to find dy sometimes rather than delta y. So if you want to find delta y, again, delta y is just the change in your y value as you shift your x value over a little bit. Really all this is saying here, this is saying f of your new x value minus f of your old x value. So delta y is what's the difference between my y values of my actual function when I change the x value slightly. Now to find dy, that's down here, we'll take the value of our slope of our tangent line at the point and multiply it by how much we're going to change x by. So note, the x value that's going into your derivative is the original x value. Then you're multiplying by how much you're going to change the x value by, and that'll give you how much your y value is going to change by in the linear approximation. So the deltas correspond to the actual function. The d's correspond to the linear approximation. So again, here it is once more. dy represents the amount that the tangent line rises or falls, so the linear approximation, whereas delta y represents the actual graph f, how much it changes. So let's see if we can compute delta y and dy. So part A, we'll call this A, we're going to switch our x value from 2 to 2.05. And there's our function there. So let's start with delta y. Delta y is just f of your new x value minus f of your old x value. So for us, delta y is going to be f of 2.05 minus f of 2. Well, when you plug in 2.05, you get about 9.717625. When you plug in 2, you get 9. So therefore, delta y is 0.717625. So that's how much the actual function's y value changed. To find dy, we are going to do f prime of x times dx. So we first need the derivative. That'll be equal to 3x squared plus 2x minus 2. And we'll evaluate that at the original. And when we plug that in, we'll get back 14. So you evaluate the derivative at the original x value. And then dy is just what the x is changing by, which was 0.05. Okay, notice it's what it's changing by. And when you multiply those together, you get 0.7. So in other words, dy is equal to 0.7. So what dy is saying is when you move your x value 0.05, the tangent line will change by 0.7 in the y value, whereas the actual function will change by 0.717625. Now we're going to do the same thing, but for 2 and 2.01. So for delta y, we'll do f of 2.01 minus f of 2, which that'll give us 9.140701 minus 9, giving us delta y equal to 0.140701. Well, in dy, we still have 14 because that was the derivative's value at the original. So that's saying the slope at the original 2 was 14. The only thing that's switching here is the distance we changed our x, which is now just 0.01, and that'll give us 0.14. So two things you should notice from this. One is that when we change our x value less, like in part B, our dy is a better approximation of the actual amount, delta y. The second thing you should notice is that dy is a whole lot easier to calculate than delta y. That's why we would want to sometimes use an approximation, because it's a lot easier. So for more complicated functions, it might actually be impossible to compute delta y. So that's why the approximations can be very helpful for us. So our linear approximation, we could always write it as our original y value plus the amount that dy changed. So in our last one, our original y value was 9. In part A, we said we changed by 0.7. So that would have given us an overall approximation of 9.7. In the second one, our original y value was y, and we had 0.14. So that would have given us 9.14. So where this is different than the others were just telling us what it changed by. This can give you your overall approximation of your y value, which is just taking the original y value from the tangent line point and adding on your dy. So if we wanted to use dy to look at the example 1 that we saw yesterday, first off, let's take this derivative. F prime of x would equal 1/2 x plus 3 to the negative 1/2, which is really 1/2 times x plus 3 to the 1/2, or you could do it as a square root. Now we want to evaluate that at the original. So yesterday we saw we put in 1 for x, because we wanted that to be square root of 4. So we'll evaluate this at 1. We'll get square root of 4, which is 2 times 2 on the bottom, so we'll get 1/4 back. So dy will be equal to 1/4. And then we wanted to, yesterday we wanted f of 4.05 was one of the ones we looked at. Well, that's really you would have to plug in, sorry, let me correct this. We wanted square root of 4.05, meaning we would want f of 1.05 for our particular function. The x amount that we changed by, we went from 1 to 1.05. So we would want to make that 0.05. And that would end up giving us 0.0125. If we then wanted to find the overall y value, so the actual value of square root of 4.05, all we've found so far is that's what it would change by from the original. So we would have to figure out what is f of 1 first. Well, when you plug in 1, you get square root of 4, which is just 2. And you would take that 2 and you would add on the 0.0125, meaning that your approximation for square root of 4.05 is really 2.0125. And if you flip back in your notes from the last video, you'll notice that that's exactly the same as we got before. So one last thing you can do with differentials is estimate errors in different measurements and how they could affect your outcome when putting it in. If you had a radius of a sphere was measured to be 21, and there could be possibly an error of 0.05, we want to know what is the maximum error in using the value of the radius to compute the volume of the sphere. Well, your volume of the sphere is 4/3 pi r cubed. When we take the derivative of that, we will get 4 pi r squared. We want to then plug in our original value here in for r. We originally measured that it was 21. And then dr is the possible change in what you could have. When I say change in what you could have, your possible error. We could be plus or minus 0.05. By plugging that in, that gives us how much that could affect the overall value. So again, this is just our derivative here, evaluated at our original measurement, just like we did in the others. So we took the derivative of 4/3 pi r cubed, plugged in the original 21, and then we multiplied by what the change in that radius value could have been. We could have either went up or down 0.05, so we plugged that in, and that means we could have a miscalculation of about 277 centimeters cubed. That's all for today's video. We'll see you next class, period.